later?
Conformational change.
There we go.
Very good. Right. So whatever conformation E is in before bound S1, it can't handle S2. S1 changes the conformation of E, now S2 combined. Right? It would be clearer, maybe, if this E had a little star on it or something to indicate a new conformation. Right? And then it might change again with S2, then you have star prime, whatever you like. Right? Does everybody see that? That's an important point. We're going to hit this in different enzymes, in glycolysis, and through the course. Lots of enzymes have multiple substrates. Then we have this kind of cool thing where some enzyme, you have two substrates and you think, well, there must be E, S1, S2 before you get any product. But here's a case where E binds to S1, forms a complex, turns the substrate into product releases, and then S2 binds. It's like you got to ping the first product away and then pong the next one comes in. So it's called ping pong kinetics. Okay. Notice that here, E prime is formed, right? So this is a little bit, this is pretty funky, really, if you think about it, right? Because now you've got free enzyme, just like you had here. What is it here that's keeping this as a prime instead? Right? It's probably some slow conformational change, because this, if this is just free enzyme, then it should be able to access that. And yet, there are enzymes where it doesn't go back to that. It stays in some conformation that has some reminder of itself, and then it binds the second substrate.
So you're saying it,
Sorry, question?
I was just wondering, like, on the top example, so if it was S2 that it bound first, that'd be a different conformational change than if S1 was bound first, and then.
It could be.
But either way, it would allow the next one to bind.
Yeah, that's right. I mean, you would be here in the ordered mechanism in that case. You could have ES2 and S1 needing the conformation of E that S2 that S2 induced. Yeah, yeah.
and then for this change back from E prime to E, is that something that would happen whether it bound to S2 or not?
Yeah, I think so. I think the idea is that it has to be slow.
Could it also be like a transfer reaction, like S1 transfer a phosphate group onto E, E is holding onto that phosphate group, S2 binds.
That's also possible. That's right. Right. So E prime could be a covalently modified enzyme. In fact, I mean, chymotrypsin isn't like this because we do have the first product go away. So chymotrypsin, you could actually argue, fits into this in the sense that part of the substrate is bound to the enzyme in a covalent enzyme intermediate. It's not really the kind of example that ping pong kinetics was developed for, but you kind of see that if you want that way. When you have two substrates for an enzyme, so let's say a hexokinase, and you want to measure the Km for ATP, right? You can't measure anything unless you have glucose in there, right? So you're measuring V as a function of time at different ATP concentrations to get the Km for ATP and the Kcat. But you have to have glucose in there, these two substrates. So how much glucose are you going to put in?
Lots.
A lot. Why?
You want to just saturate.
Saturate for glucose, that's right. Because then the enzyme will be able to get to its Vmax, right? If you put in an amount of glucose, say that equals to glucose Km, now it's only half saturated for glucose approximately, right? So now your Vmax that you measure is going to be limited by the fact that the enzyme population is only half bound to the other substrate, right? So all of a sudden your Kcat starts coming out low, and you're like, huh, this enzyme is, you know, somebody dropped acid in my enzyme tube, or this enzyme doesn't work. It's because you didn't put enough glucose in.
Is there like a limit or a specific number of how many substrates there could possibly be? Kind of doubt.
3 substrates are common. 4 are uncommon, unless you want to count like a magnesium as the 4th one, something like that. But yeah, there's a practical limit. I don't think there's any examples of more than 4. Right, so we're going to hit examples of different classes of enzymes with lots of different substrates, and I'll refer back to this stuff. Okay, so I'm going to say a few things about inhibition before we go on to talk about allostery. So, there's two kinds of inhibition. There's reversible and irreversible inhibition. And irreversible inhibition comes in two kinds: covalent modification or transition state analog. Right? So I'll show you covalent modification on the slide. Transition state analog is a situation like this, for example. We talked about this already, where if you have a phosphoryl transfer reaction, the transition state is pentacovalent on phosphorus, right? And what if you had a compound like vanadate, which is VO5 and stable, and you feed that to an enzyme that goes through a pentacovalent phosphorylated intermediate, right? Throw in enough vanadate, it might bind right where that phosphate is, because the enzyme likes to bind trigonal bipyramidal molecules with oxygens all in the sphere, which VO5 is a very good analog for that. So unless the enzyme is super requiring of the P instead of the V, right? Vanadate can be a very good transition state analog. It can be so good that it'll basically inhibit the enzyme and it'll never come off. It'll be binding so tightly. So irreversible, if it's not covalent, it means it's binding very tightly. But covalent means that, as you would expect, there's a covalent reaction. So here's chymotrypsin, and here's diisopropyl fluorophosphate, DIFP, which is this puppy here, with a great leaving group here. So if the serine attacks this phosphorus, it forms this. This guy is, that chymotrypsin molecule is dead. Okay. That's blocking the active site. Substrate can't bind anymore. It's never coming off. Right? I mean, maybe you could get a hydrolysis and then get it to come off eventually. But for all intents and purposes, for the time scale of the reaction it's supposed to work on, this is an irreversible event. Okay. DIFP used to be available. I hope nobody's using it anymore. It's very toxic. It used to be in labs because a lot of labs used to work on chymo. But not recommended to use that. There's other ways to inhibit serine proteases without having to use toxic like this. Okay, so the other kind of inhibition is competitive, or sorry, I should say reversible. And reversible inhibition can be competitive or not. I'll just say not competitive because they're different classes, which I'll get to in a moment. Right. With competitive inhibition, the Michaelis-Menten equation is modified a bit. And we're not going to go through the derivation. The book actually gives you modified Michaelis-Menten equations for different kinds of inhibition that are of reversible inhibition. And I'm only going to give you this one. And I don't, well, you should probably remember it, but it's not. Okay, so instead of Km, we have this parameter called alpha Km. Right? And alpha is 1 plus the concentration of inhibitor divided by the inhibition constant. Right? So we're talking about competitive inhibition here, right? And reversible. So some small molecule probably is getting added in there. It's going to compete with the substrate. Competitive means compete with substrate. It's going to inhibit the enzyme, but it's going to be reversible. Okay? It's not going to kill the enzyme molecule forever, but it is going to stop the enzyme from functioning well on the substrate. And depending on the kind of reversible inhibitor, it'll stop the enzyme from working well in different ways, right? That is to say, it'll affect Km or Vmax or both. Right? So Ki is this. Just so you have the definitions of these things. This is as far as we need to go. So Ki is like a Kd for the inhibitor. That's it. Alpha is a parameter that if you have no I, alpha is just 1, right? If I is 0, and just everything we've talked about so far, I is 0. We haven't had any I's in there. So if I is 0, alpha is 1, and this is 1, and so it's Michaelis-Menten. That's it. right? So if the concentration of I equals the Ki, right, then alpha equals 1 plus 1 equals 2, right? And then the apparent Km is 2 twice what it was, the apparent Km, right? So Km went up for a competitive inhibitor, right? If you accept this equation, which I'm asking you to accept without deriving it. This is how competitive inhibitors work. So it's better to look at it on the slide so you can get a sense of it structurally. Because, you know, that's like kinetics equations, not so intuitive necessarily. But here, we've got an enzyme that binds substrate. Oh, it could also bind inhibitor. Notice that the inhibitor is binding at the same place that the substrate does. S and I go to the same active site. Now, if you just give it a lot of substrate, more and more and more, it will depend on the relative affinities of S and I for that same active site. But eventually, you can swamp out the I. Right? And if you can do that, that means you can get the enzyme can go just as fast as if there was no I, as long as you give it enough S, which means there's no effect on Vmax. Right? No effect on Vmax. On the other hand, you have to give it all this S to get there. So the amount of S you have to give it to get to half Vmax is obviously a lot more than it was if you didn't have any I at all. So your Km is up. Do you see that? This just comes right out of the competition. Questions? So this is the most important form of inhibition, and this is what I want you both to think about the most when you think about inhibition, because we can understand it in these terms. We can understand what it means to swamp it out. We can understand why there's no effect on Vmax, but there is on Km. And we can think that the inhibitor binds non-covalently in the active site, non-covalently and reversibly in the active site.
If the Km changes like so, in this condition, does that mean that if you double the substrate, it will affect the or it doesn't?
It doesn't quite work like that. Depends on what the Km is and what it means to double it. But you'll move up the curve. But that won't be enough to swamp it out completely yet. Now here's where the Lineweaver-Burke comes in. Right, so here's the Lineweaver-Burke plot of 1 over V versus 1 over S. Okay, so this is the plot I showed you before, which is one line. Okay, so there's the equation, except now it's alpha Km over Vmax because there's an inhibitor in there. Right, so if alpha is 1, meaning no inhibitor, right, there's the line. No inhibitor, right? And if alpha is 2, Vmax is unchanged, so 1 over Vmax is unchanged, right? And minus 1 over Km goes this way, which means that Km's going up. Right? 3, more of the same. So you get this set of curves. So this was a big deal at the beginning of enzymology. People were characterizing inhibitors. They wanted to know, well, what kind of inhibition is it? They would measure all these data with different amounts of I, right? I mean, people would just spend years doing this kind of stuff. And they would eventually come out with a plot like this, and be like, oh, my inhibitor is competitive. Okay. So the other kind of inhibition is uncompetitive. And uncompetitive inhibition, right, I should say, is one of 3 different kinds of inhibition that is not competitive. Right, so uncompetitive, there's also non-competitive and mixed. Okay, so this is just a lot of terminology here. I don't really care that you keep these distinctions straight among those 3. You should know that they're all different from competitive. And the common feature of them is that I is not binding where the substrate binds, is binding somewhere else. Okay? There's going to be some EI complex, there's going to be some KI. It's just that there's another binding site somewhere else. And that's how it has its effects. So now, rather than having no effect on Vmax and a big effect on Km, it can have different kinds of effects. Okay? So we could have an example where we have bottom part of this. Reversible inhibition, non-competitive, do not bind active site. So here's the three kinds: uncompetitive, mixed, and non-competitive. So this gets very complex and highly non-intuitive, to put it mildly. Like, I have no intuition about this stuff. Right, so uncompetitive, it binds only to ES, lowers Vmax, and lowers Km. Lowers Km is like a good thing. So what's up with that? Right? And why should it be that those two parameters are affected that way if it binds only to ES and not to E, right? So substrate has to be there first. So what's up with that? If anybody understands it, let me know. Mixed inhibition binds either E or ES, has these effects. Non-competitive binds E or ES, lowers Vmax, no effect on Km. Right? I'm trying to, this is a little drawing here. It didn't show up at least. Substrate and inhibitor down there. Inhibitor's binding somewhere else. Okay? So I don't care that you keep these things straight because there's no productive way to really understand it well. And in the end, it represents the kind of enzymology to characterize these different kinds of reversible inhibitors that are not competitive and distinguish the classes of those. Almost nobody is doing this kind of stuff anymore. Right? It's a tribute to the traditional-minded nature of the textbook authors that they continue to keep this stuff in there. Questions? All right, yeah.
If uncompetitive is lowering Vmax and then lowering Km, then would that kind of inhibition be lowering the affinity of that substrate to the enzyme?
If it's lowering Vmax and lowering Km, qualitatively we would say that the affinity is actually getting better for the substrate. To the extent that Km is mimicking the affinity, we would say that it's actually making it tighter. Right, so you would think that these effects are somehow being transmitted through the structure would be the most likely way to think about them, although there's apparently ways to do it in which they're not transmitted through the structure, but I don't understand what they are. Yeah.
So is the takeaway from this basically that with not competitive inhibition, like you're not binding the active site, and whether it's binds the enzyme or the enzyme substrate, you can have a bunch of different effects?
Yeah, that's it. Yeah. There's no way I'm going to ask you the difference between these three things. Right? I will ask you. I expect you to know what competitive means, right? And then if it's not that, then you know there are complicated effects. It could bind E or ES. It could affect one or both parameters in one way or another. I mean, what's the point of memorizing that kind of stuff? All right, allosteric. This is a classic example of where allosteric works. Feedback inhibition in a metabolic pathway. The product of the pathway is isoleucine, a common amino acid. The beginning point of this particular pathway happens to be threonine. Threonine did not appear by magic in the middle of the cell. It got made from something else, of course. But this is like a little piece of the metabolic map. And what's going on here is this dotted line up the left side is showing you that isoleucine binds this enzyme called threonine dehydratase, which is the first step in which threonine is dehydrated. So you can imagine that it takes water away from OH and H and forms a double bond in there. Never mind what it looks like. A will look something like that. Right. So this is an example of, which we'll get into, heterotrophic allosteric inhibition, in which isoleucine binds reversibly and non-covalently to a distant regulatory site, right, not the active site. Right? And so the activity of threonine dehydratase is obviously very sensitive to how much isoleucine there is in the cell. Right? If there's a lot of isoleucine in the cell, why bother making more? Right? Let's turn it off. How are we going to do that? We're going to have isoleucine itself bind the first enzyme in the pathway to make it. Right? Why not have it bind one of these enzymes in here? Well, then you're wasting this power to make these intermediates. If you don't have any other use for them, which you probably don't, then why